All right, we're going to begin with sequences, and what we're examining is it's basically any kind of pattern, whether or not it's in theory or it's applied. It's just a list of numbers, and they become more and more important as you get into calculus. So just to get you practicing understanding sequences, they start with what appears to be function notation, where n is your x variable. That's why it has this statement of saying that's the domain. So there's a couple other ways of writing it as well. Instead of writing a of 1 like this, sometimes we write it as a subscript 1. So what it means, though, is you're plugging 1 in for n. So I'm just going to write equals here to keep it kind of short and sweet, that if you plugged in 1 for n, 2 times 1 is 2, minus 1 would be 1. So that's your first term in this sequence. The second term is plugging 2 in for n. Well, 2 times 2 is 4, minus 1 is 3. And then the third term, 2 times 3 is 6, minus 1 is 5. And what we're going to learn is some different types of sequences. So if you notice in this first one, we had a common difference. We were adding 2 each time. That is something called an arithmetic. When you're adding the same number, it's spelled like arithmetic, but we do pronounce it arithmetic. It's an arithmetic sequence. So what you'll also learn in this problem is the sigma notation. So this means the sum of, it's the Greek letter sigma, it's a capital sigma for anybody that's curious, and we use that to sum things together. So pay close attention. We do use different letters. I know it's very tough to see. Let me just write it out for you. It's written as this Greek letter. And they use I, J, K, different letters like that, from 1 to 5 of a sub I. So this is not the imaginary number I. What it means, though, is you're doing a sub 1, because that's the first number, plus there's your sum. You continue on in ascending order, 1, 2, 3, until you get to the top number. That's how we read sigma notation. So we already found a few of these numbers. For instance, we found that a sub 1 is 1, a sub 2 is 3, a sub 3 is 5. Well, if we wanted a subscript 4, we would plug in 4 in here. 2 times 4 is 8, minus 1 would be 7. But if you notice the pattern going on, 1, 3, 5, 7, what do you think the next number will be? 9. And then the evaluation of this would be, well, 4 plus 5 is 9, plus 7 would be 16, plus 9 would give me 25. Now, I am also a realist. I do know that your calculator will do problems like this. I'm just hesitant to show you right now. I do want to point out, though, that your calculator can do things like this if you want to investigate. The problem is when we get to what are called recursive definitions. So what does it mean to be recursive? Is you need to know the previous term in order to know the next one. Okay, so I know this is confusing at times, so stick with me. This phrase is referred to as the n plus 1th term. So what that means is let's say we know a sub 1 is negative 2. I'm going to write that down because it tells you. Well, if I ask you for a sub 2, what I'm saying is that n plus 1 is equal to 2, which means, maybe I'll write that out, maybe in a different color, that n plus 1 is equal to 2, so then n must equal 1. So this n plus 1th term is equal to the nth term, which would be a sub 1, and then you add 5 to that term. So if that's what makes it recursive, is we have to know the previous term, and then when we add 5 to it, then the second term would be equal to 3. So let's continue that pattern on. A sub 3, well, if I think of it this way, that n plus 1 equals 3, I'll even write that out, then n needs to equal 2 in that problem. So we have to take a sub 2 and add 5 to it. So a sub 2 is equal to 3. Well, if I add 5 to it, I get 8. And maybe I'll even emphasize with a very different color. You can see from the first term I add 5 to get the second term. That's what makes it recursive. The second term I add 5 to it to get the third term. So what do you think a sub 4 will equal? Well, if I add 5 to that, I'll get 13. And what do you think a sub 5 will equal? Well, if I add 5 from the previous term, I'll equal 18. So without giving you a formula yet, we will get to a formula, we can actually notice a pattern. I accidentally changed colors, I think, to figure out what the 20th term would be. And there's a little hint right here, so you might be able to actually think of what the correct answer is without me giving you the clue. And here's our issue, is if I ask you for a of 20, based off of our recursive definition, you need the 19th term to figure out the 20th. And in order to figure out the 19th term, you need the 18th term. So that's why we have this hint. How many times would we have to add 5 to negative 2 to get to the 20th term? Now be careful with this, because the second term only added 1 5. The third term added 2 5s to that negative 2. The fourth term added 3 5s. So let's put it this way, a sub 20 must add 5 19 times. And I hope you noticed that pattern before I just gave it to you. So if you notice a sub 5, there's 1, 2, 3, 4 5s added to it. So you subtract 1 from it. So there is a formula, which I might as well just give it to you right now, is if you want a sub n, you take the very first term that they give you, and then you add the common difference, that's what this d value would be, the common difference that's being added, times n minus 1. We'll come across that formula again later. You might want to put that in your back pocket for right now. So the correct answer for a sub 20 is equal to the first term, which was negative 2, plus the common difference, and plugging 20 in for this n, 20 minus 1 is 19. I don't know how many of you would need a calculator for that, because 5 times 20 would give me 100, so 5 times 19 must be 95, and adding negative 2 to that should give me 93. So again, this has been an arithmetic sequence because we're adding the same number over and over again. So as I look at the next one, if you notice, it's not a common difference. We're not just adding 5 each time. This time we are multiplying each term by 2. This is called a geometric, and we'll get to more of these in the future. And instead of calling it a common difference, this is called a common ratio. Again, I'm just kind of warning you of things in the future. So when they ask you to come up with a recursive definition, there's 2 things that you need to do. The first is to start with the first value. So tell me what a sub 1 is equal to. Well, the first term is equal to 5. That's from right there. So that's part of your answer, is the recursive definition. Now the next part is telling me what the next term needs to equal. So that's where we write the n plus 1 term. So like if I'm asking for a sub 2, then a sub 1 would be the previous term. I know this is difficult to think about, but that's the pattern going on, is we want to look at the next term based off of the previous term, and in this pattern it would be multiplied by 2. And you can explore a little bit on your own. I'll just change colors just to show you. If I asked you for a sub 2 then, well then that's saying take the a sub 1, which is 5, and multiply by 2. Do you still get 10? And then if I look at a sub 3, so n plus 1 equals 3, then a sub n would be a sub 2. Is it still times 2? Well, 10 times 2 is 20, so yeah. And you can continue on just to make sure that you have the right answer. And I'm really emphasizing this so you understand the recursive definition, because it is difficult, you know. And if you're thinking this is really, really easy, then that's good. I've had a lot of students struggle through this, so feel free to write down your questions and bring them to class. So looking at the next one, again, if you're still struggling, don't be scared to ask questions, because now it's asked completely differently. Because all the first two problems I've been talking about, or the exercise 2 and 3, I've been doing n plus 1 here. Well, this time I put t sub n, and over here I put t sub n minus 1. So I wrote it differently, but it is still recursive. Why? Well, if I know the first term is 2, and I'm asking you for the second term, so t sub 2, well, plug in 2 for n. What's 2 minus 1? It's t subscript 1 squared plus 2. I hope you're seeing the pattern that's going on here, because now I can actually figure that out, because t subscript 1, the first term, is 2. 2 squared is 4, plus 2 gives me 6. So t sub 2 is equal to 6. But I'm not asking for t sub 2, I'm asking for t sub 4. Well, let's figure out what t sub 3 is first. So again, I'm plugging 3 in for this n. Well, what's 3 minus 1? It's 2. I'm just following the pattern, and I'm plugging 6 now in here. Well, 6 squared is 36, plus 2 is 38. Now be careful, that was t sub 3. I don't want t sub 3, I want t sub 4, so that's not right. And at this point, I'm not going to be able to do this in my head. But it is the third term squared plus 2. I just don't know what 38 squared is when I plug that in right here. So I'm going to go to a calculator. 38 squared plus 2, 1446, and lo and behold, that was one of my options. Okay, I'm going to stop right here just because I'm halfway through the notes, and I'm about at the end of my 15 minutes. So I'll see you in the next video to continue on with the rest of these notes.